Greetings from Easy BTech. In the last class, we have been learning about Compton effect definition, that is, phenomena of Compton effect, wherein we have seen that a high frequency photon collides with an electron which is at rest position, and then the photon transfers its energy to electron. As a result, photon gets scattered with an angle of phi in the direction of incident, and electron recoils with an angle of theta made with the direction of incident. So now, when the photon has interacted with this electron, the frequency of the photon has been reduced as part of the energy has been transferred to electron. As a result, the frequency of the photon has been reduced to mu prime from mu. This change in the frequency of the scattered photon with respect to incident photon or the wavelength is simply defined as Compton shift. So now we will check with this Compton shift calculation. So let's have a look over Compton shift. So if you look for your Compton shift, we are saying here the change in the frequency or the change in wavelength. So to have a clear understanding and make our calculation very simple using easy BTech concept, I'm going to give you a small table which helps you for calculation throughout. So let's have the table. We are having two parameters. One is before collision situation. The second one is after collision situation. So I'm going to draw it in the same way. One is before collision and another one is after collision. So before collision and the second one I'm saying is after collision. So before collision, I have once again two parameters, two particles, that is photon and electron. I'm having here photon and electron. Similarly, even after collision, I once again have a photon and an electron. So we are saying here the photon and electron are with the different positions. That is, photon is moving but electron is at rest position in the before collision situation. So we will look into the parameters of energy and momentum. In both the situations, that is before collision and after collision, for photon and electron. So let's look over here for that. If I look for photon, it is having a frequency of mu. So the energy is given as h mu. And we are having the same photon to be possessing a frequency of mu prime after collision. So I'm having its energy to be considered as h mu prime. And next, if I look for the photon, since my energy is h mu, I can write my momentum as h mu by c. Similarly, after collision, I can write my momentum as h mu prime by c. Now we will go for electron. Electron is having here an energy as m naught c square, where m naught is called as rest mass. After collision, electron is moving, so it is having energy as mc square, where this m is equal to m naught by root of 1 minus v square by c square. Similarly, now if we look for the momentum of electron, our electron here, if you look at the figure, electron was in rest position before the collision situation. So I'm having here its momentum to be 0. But after collision, it has recoiled with an angle of theta. So it is having here momentum as mp. So now we are going to use the principle of conservation of energy and principle of conservation of momentum. According to the principle of conservation of energy, we have energy before collision to be equal to energy after collision situation. So now I'm going to use here conservation of energy principle, conservation of energy. So when I go for energy conservation, how much is energy have it before collision? Just we can have from this table. It is complete energy is h mu plus m naught square c square. So I'm having h mu plus m naught c square. So if I look for energy after collision, how much I have? H mu prime plus mc square. So I'm going to use here equal to h mu prime plus mc square. So to simplify our equation, I'm going to take here h mu prime onto the other side and rewrite the expression here. So when I rewrite with my expression, it becomes m c square to be equal to h into mu minus mu prime plus m naught c square. Square this equation and then number it. On squaring, I have m square power c power 4 equal to here a plus b whole square form. So I get here h square into mu minus mu prime, that represents a square, and 2ab, which could be written as here 2h m naught c square into mu minus mu prime plus b square, which is nothing but m naught square c power 4. Now, if you look at this equation, this mu minus mu prime is in the form of a minus b whole square. So, let us expand that equation. Then here it becomes h square into mu square minus 2 mu prime plus mu prime square plus 2h m naught c square into mu minus mu prime plus m naught square c bar 4. So now we are going to number this equation as 1. We have completed now conservation of energy principle and obtained the value for m square c power 4. Now we are going to use conservation of momentum principle. So when I use here the momentum of conservation of principle, have a look over your figure. Before collision, I have photon whose frequency was mu and your electron was at rest. So we are having here only one direction, the incident direction, which is assumed to be x direction. So I have here two directions. One is with respect to x and another one is with respect to y. Similarly, here for photon and also electron, I have two directions, x and y. Horizontal component, as we know, is generally represented by cos. Since recoiling angle is theta, I am writing it as cos theta. Similarly, vertical component is given by sin theta. And here for photon, since my scattering angle is phi, cos phi, and vertical component is sin phi with phi as a scattering angle. Now the momentum has been resolved. So before a collision, the momentum of electron is 0. But when I come for your photon, it is h mu by c. But now if I look at the situation that we are having before collision and after collision for momentum, you are having your momentum to be represented for your electron as mv. So I'll have here mv cos theta along x direction for electron, and for photon it becomes mv cos phi along horizontal direction. Similarly, if I look for vertical component, it becomes sin theta into mv for electron, and when I talk about photon, it becomes mv sine phi. So now I will apply conservation of momentum principle along x-axis, and then I'll apply for y-axis and add these two to get the total momentum. So remember this, we are having here horizontal component for electron as mv cos theta and its vertical component is mv sin theta. Similarly, horizontal component for photon is taken as mv cos phi since your phi is the scattering angle. Similarly, vertical component we are having it as mv sin phi. So let's have conservation of momentum along x-axis. So I am going to use here with conservation of momentum. The before equation was for energy, now we are going for conservation of momentum. So as I said, photon is traveling in the direction of incident in the before collision situation. So only I have x-axis for photon and electron is at rest position. So I am going to have the 0. For photon it is h mu by c and for electron it is 0. So I have h mu by c plus 0 to be equal to h mu prime by c into, for photon I am writing, for photon my scattering angle was phi. So I am writing cos phi plus mv. For electron we are having mv to be the momentum and my recoiling angle as theta. So I am going to write mv cos theta. So from this equation, I can have a simple simplification to be done, that is h mu equal to h mu prime cos phi plus mvc cos theta. The same equation is rewritten as taking my h mu prime cos phi onto the other side. My equation reduces to mv cos theta to be equal to h into mu minus mu prime cos phi. Now square this equation. On squaring, how does that equation reduce to? It becomes m square v square c square cos square theta, m square v square c square cos square theta on LHS. And if you look at your RHS, we are having there h into mu minus mu prime cos phi. So it becomes h into, since it is squaring, h square mu square minus 2 mu prime cos phi plus mu prime square cos square phi. So now I am going towards y direction. This all we have represented along x direction. So we will just mention that along x axis here to have a little clarity. Now I'm going to look over y axis. Along y axis, I do not have any momentum to be observed in before collision situation because the photon is not moving in the y direction and electron is at rest position. So going for the other one, that is after collision situation. I have here the momentum of my photon to be expressed as h mu prime by c. Since it is a vertical direction, I am going to write it as sine phi. And coming for the next one, electron. We are having electron here to be taken as mv sine theta because my scattering angle is theta. Sorry, recoiling angle is theta for electron. For photon, my scattering angle is phi. So I am having h mu prime by c sine phi plus mv sine theta to be equal to 0. The same thing I am going to have it to be written by squaring the equation. So I'll write this as m square v square c square sine square theta to be equal to h square mu prime square sine square phi. So if you look this, you can number this as 2 and this as 3. To get the total momentum, add 2 and 3. So if you look your LHS of both the equations 2 and 3, what is there? It is m square v square c square cos square theta, and this is representing m square v square c square sine square theta. So my LHS I have m square v square c square as common, written as cos square theta plus sine square theta to be equal to h square mu square, h square mu square. The second one is minus 2 mu prime h square minus 2 mu prime h square cos phi. And what is happening with the third one? We are having here h square mu prime square cos square phi, and we also have here h square mu prime square sine square phi. So I'll take h square mu prime square as common. Then what will be left for me? So if we look at this equation, now we are having cos square theta plus sine square theta, which is equal to 1. And similarly, I have cos square phi plus sine square phi equal to 1. So using that substitution, I'll be having the expression to be m square b square c square to be given as, I can take my h square also common. So h square into mu square minus 2 mu prime cos phi plus mu prime square, because once again cos square phi plus sine square phi equal to 1. I'm going to number this equation as 4. Now subtract 4 from 1. So what is our equation 1? Our equation 1 is about energy. This is the equation of 1, m square c power 4. So we will rewrite that equation and then subtract so that it becomes easy for us. So I have the same equation to be taken here, which is m square c power 4. How much was your equation with the continuity we are having there to be represented as h square into mu square plus mu prime square minus 2 mu prime plus m naught square c power 4. So you are having here m naught square c power 4 m naught square c power 4, and it is also followed by 2h into mu minus mu prime into m naught c square. This is equation 1. Now subtract equation 4 from 1. So m square c power 4, and you will be having it to be m square minus m square v square c square. So if we look at these two equations, we are having m square c square as common. So let's take that m square c square as common. So you are having m square c square common. Then I have c square minus v square. Now look here, you are having with your equation 1 h square into mu square. The same h square mu square is there even here, but this is plus and this is minus. And also I have h square mu prime square. Along with minus, it becomes here h square mu prime square. So these two can be cancelled. Then the remaining terms will be left for us. So we will write the expression now once again here as h square into, I'll first write this expression, mu square plus mu prime square minus 2 mu prime plus m naught square c power 4 plus 2h into mu minus mu prime m naught c square with the minus h square into mu square plus mu prime square minus 2 mu prime. Don't forget with this cos phi. Okay, it is 2 h square into mu square plus mu prime square minus 2 mu prime cos phi. So this is what you are having. Now what will happen? I can have this mu square minus 2 mu prime square mu prime square. Then what will be left over for me? H square into minus 2 mu prime. Here also I have minus of minus plus h square into 2 mu prime into cos phi. Then write the remaining things. M naught square c power 4 plus 2h into mu minus mu prime m naught c square. When I rewrite this expression, I am getting this. Now I am going to take 2 mu prime h square as common. 2 mu prime as with h square as common. So this becomes 2 mu prime h square as common. I'll take with a negative sign. Then it becomes 1 minus cos phi plus m naught square c power 4. So still what do I have here? 2h in m naught c square into mu minus mu prime. Number this equation as phi. Previously we have seen that m is representing as variable mass. So how are we relating that with the rest mass? M equal to m naught by root of 1 minus v square by c square. So the same thing I can write here. If I square this expression, it becomes m square equal to m naught square c square by c square minus v square. Now use this m square in equation number 5. Use this m square in equation number 5. So what is your m square? M naught square c square by c square minus 5 v square. So if I substitute with that, it becomes m naught square c square by c square minus v square. I substituted only for m square. Then I have it to be followed with c square and also it to be given with c square minus v square. The remaining expression is as it is. So I am rewriting the equation of RHS m naught square c power 4 minus 2 mu prime h square into 1 minus cos phi. Still what do I have? 2h m naught c square into mu minus mu prime. So if you look at this expression now, c square minus v square will be cancelled. So how much will be left for us? M naught square c power 4. On RHS, m naught square c power 4 minus 2 mu prime h square into 1 minus cos phi plus 2h m naught c square into mu minus mu prime. So I can observe that on both LHS and RHS I have m naught square c power 4. So I'll cancel this to m naught square c power 4. Then my expression becomes 2 mu prime h square into 1 minus cos phi to be equal to 2h m naught c square into mu minus mu prime. Now I'm going to simplify this. 2 and 1h get cancelled. I'll take this mu prime onto the other side. Then it becomes h into equal to m naught c square. Since I'm simplifying here, mu by mu prime. Then what will happen? One mu will be cancelled and I'll be left with 1 by mu prime. Similarly, mu prime by mu prime. Mu prime will be cancelled and I'll be left here with 1 by mu. So here I'm having this m naught c square also to be taken onto the other side. Then I can write here it as h by m naught c square into 1 minus cos. So this is, we are having 1 by mu prime minus 1 by mu equal to. Now I can take 1c onto the other side, or I can simply have it to be in terms of wavelength, directly writing mu is equal to c by lambda. So if I write here mu is equal to c by lambda, mu prime will be c by lambda prime and mu is simply c by lambda. Mu equal to c by lambda. So then equation becomes lambda prime minus lambda equal to h by m naught c into 1 minus cos phi. What is your phi? Scattering angle. So cos phi, when I say here, phi is representing my scattering angle, and I can rewrite this 1 minus cos phi as 2 sine square phi by 2. So it becomes 2h by m naught c into sine square phi by 2. So lambda prime minus lambda I said. What is this lambda prime minus lambda? It is going to represent as the change in the wavelength, which is simply given as. So using this, we can calculate Compton shift. So we can expect numericals on this formula. Given with your scattering angle, you will be asked to determine Compton shift. Otherwise, if you are given with your Compton shift, we can take down with your scattering angle. As we know, h is a Planck's constant and m naught is going to represent the rest mass, c is the velocity of light. Since these are the fixed values we have, we can easily calculate the change in the wavelength of a scattered photon. So this is how we are having Compton shift to be calculated. So hope that this derivation from Easy BTech will definitely help you out. Thank you.